Hi, I'm Jonathan Braden. I'm a senior research associate at the Canadian Institute for Theoretical Astrophysics in Toronto. And today I'll be talking about how we can build experiments of the early universe using Bose-Einstein condensates. And before I get going, I just want to thank the organizers for inviting me to give a talk. Last time I participated in Cosmo from Home, it was a really great experience. So I'm looking forward to this year's version. Okay. So before I dive into details, just a quick overview of what I'll be talking about today. So I'll start with giving some context, specifically context about what parts of early universe cosmology I'm interested in and inflationary cosmology. And the things I'm going to be focusing on here are sort of epochs in the very early universe where we think nonlinearity played a fundamental role in the dynamics of the fields. And the two specific dynamical things I'll be discussing there are preheating, which is sort of how inflation ends, and then phase transitions, so vacuum decay, which can occur at various times in the very early history of the universe. Then once I've gone through that, I'll give a brief overview of how we can use Bose-Einstein condensates as analog systems for cosmology, and specifically how there's a mapping between sort of the equations that we think govern the early universe and the equations that govern the Bose-Einstein condensates. And then I'll give some specific examples of how we can set up a laboratory BEC system to kind of mimic a lot of the properties of preheating or of inflation dynamics. And I'll give a little bit of an overview of how we can also study vacuum decay with BEC systems as well. All right. So just to put into context what I will be talking about, my motivation for this work. So we've got here our standard cosmic history, and I'm an early universe cosmologist. So I'm mostly interested in the stuff on the left side of this diagram. Okay. And for the purposes of this talk, there's a few key epochs that I'm going to really focus on. So the first one is in our standard model of cosmology, at very early times, the universe was undergoing inflation. So it was expanding exponentially fast. And this epoch exists to set up the primordial density perturbations that act as seeds for structure formation in the subsequent history of the universe. And we know that at some point inflation had to end, and out of that is supposed to come a very hot bath of particles whose temperature is above the temperature required for Big Bang nucleosynthesis and potentially much, much higher. Okay, and so we know that we have to connect these two epochs, inflation and the standard hot Big Bang. And that I'm just going to call preheating or reheating. Okay, and so that's one epoch I'm going to focus on. And then another one is that after this very hot bath of particles emerges, a lot of ideas in particle physics suggest that the universe may have gone through a sequence of phase transitions as it was cooling down. Okay. And so it's possible that in this sort of like hot thermal bath before the CMB forms, before you have BBN, that we may have had interesting nonlinear field dynamics occurring. And similarly, before inflation started, we think there was a singularity or something that smoothed out a singularity, Big Bang if you want. And so one model for what the Big Bang was this false vacuum eternal inflation model where on very, very, very large scales, the universe is trapped in some a metastable minimum and it's nucleating bubbles. And inside of one of these bubbles is where our entire observable universe exists. Okay. All right. The key feature of all of these epochs that I just reviewed is that they're very, very nonlinear, okay, and non-equilibrium, and non-perturbative, and they involve quantum fields interacting with gravity, okay? And so these are the kind of things I really, really am interested in. Like, how does nonlinearity affect the evolution of the universe, okay? And so now let me just quickly review in a bit more detail what these preheating and phase transition dynamics look like. So let's start with preheating. All right. So what we're really discussing here is starting the standard hot Big Bang. So in the standard view of cosmology, as I said, preheating is linking up the inflationary phase with the standard hot Big Bang, where there's a very hot thermal bath of particles. Okay. And so our standard view of inflation is that it was in many ways very, very simple, right? It's sort of cold. It's zero temperature, which means there's no entropy, at least on sub-horizon scales. On super-horizon scales, that's a different question. And there's very, very few active degrees of freedom. You know, the way we usually discuss inflation is as, you know, there's some field value, it's homogeneous everywhere, and it's interacting with an FRW metric. So there's like a number that's time dependent that we have to track. And what has to happen is at some point we have to get a bunch of particles, okay? And those particles have to be very hot, and therefore they have to have a lot of entropy, okay? And because you have a ton of particles, they're all flying around, there's a huge number of active degrees of freedom in the system as you go from this transition between inflation to the standard hot Big Bang. And that involves a huge amount of entropy production and information processing of your quantum fields. In fact, in some sense, you've created all of the entropy stored in particles during this event. Okay. And a different way to think of this is really we're trying to understand what is the recipe to make the cosmic soup of particles that exist in the universe at very, very early times. Okay. So in order to make any progress here, we need to have some sort of model. We need a Lagrangian. And so I'm going to take the standard view of most early universe cosmologists and say I'm going to model this transition as a bunch of relativistic scalar fields interacting with gravity. Okay. And so the way I'm going to think about it is during inflation, so I've got some potential for these fields, and there's one special field called the inflaton. Okay. And that field is displaced from its minimum, and it's sitting out on a potential somewhere. And what's happening is it's slowly rolling along the potential. Okay. And while it's out here, the universe is inflating, and I'm generating all the super-horizon perturbations that are eventually gonna form the large-scale structure of the universe. Okay. Now the field's rolling, and eventually, at some point, it will reach a point where the potential force wins out against the effects of Hubble friction. Okay. And at this point, inflation ends, and the exponential expansion of the universe starts, and the field starts oscillating around a minimum. Okay. And then what has to happen is all that energy that's stored in the oscillating field has to be deposited into the standard model. And so this is the epoch of reheating or preheating. And the thing that's very interesting about this is if I write down a microphysical model with a Lagrangian for fields, and then I ask what happens if I let the fields be sloshing around in some minimum, well, this picture is sort of homogeneous. I said there's no fluctuations, right? But that violates the uncertainty principle. So I can't, quantum mechanics doesn't let me make a field completely homogeneous. There have to be quantum fluctuations on top of it that are spatially inhomogeneous. Okay. And when you include those, what you will find is there are a huge number of instabilities that can exist in these fluctuations. Okay. So you will tend to have bands of wave numbers that are growing exponentially fast. And this is a very, very generic thing that will happen. And so what we think is that the way that end of inflation actually works is that you start from a state where you've got a bunch of nearly homogeneous fields and just small quantum fluctuations. And then the dynamics of that system after inflation ends will cause the fluctuations to become very large, okay, at linear level. All right. And so the theory of this was worked out kind of in the early to mid 90s originally. And this is where the term preheating came from. So the idea is we're gonna treat those quantum fluctuations as being very small, so we can expand the field like this and treat delta phi as some linear perturbation. If you do that, then what you will typically have is an equation of motion for these fluctuations that looks something like this, okay? Which, if you look at it, is basically a harmonic oscillator. The key thing here is that V double prime, which is the curvature of the potential, is evaluated at whatever the mean value is. And the mean value of that field is oscillating in time, which means that this term is oscillating in time. And so I have a harmonic oscillator with a time-dependent mass, and that mass is oscillating in time. So it's well known that when you have harmonic oscillators like this, that there tend to be exponential instabilities for certain choices of k and parameters that go into your potential. And so what I'm showing in this figure on the left is just one example of solving this equation for a particular choice of potential and k, where we see there's this exponential growth in the modes. Okay, And so what will happen is the initially small quantum fluctuations will grow exponentially fast in linear perturbation theory, okay? Now, that's all great and interesting, but the really interesting thing is the fact that you started with some small fluctuations, you made them grow very fast, eventually they're going to be big, and then they will interact nonlinearly with each other. So you get back reaction effects sort of that affect the mean field dynamics, but you also get rescattering effects where you have mode-mode coupling between lots of different modes. Okay, and so a full treatment has to include all of this dynamics in it, all right, and requires doing lattice simulations to study sort of what's the end state of this instability. And so there's kind of a standard way of doing this if you want, which is, of course, we would like in a perfect world to solve the full quantum field theory problem. Unfortunately, I'm not nearly smart enough to solve an exponentially difficult problem in an infinite dimensional space. So we have to make some approximations. And the approximation that is generally made is to say, okay, the thing that I was really missing was I didn't have those initial fluctuations in my description of the fields as being homogeneous. So what I'm going to do is I'm going to take samples of the quantum fluctuations. Okay, so I'll grab samples of a Gaussian random field for phi in its time derivative. And now I'll say that's a realization of the quantum vacuum. I'm now going to treat those as statistical fluctuations, and I'll sample over the statistical fluctuations and run forward in time. And then from that initial draw of the quantum fluctuations, I'll just solve the full nonlinear equations for the field coupled to an FRW metric, including full back reaction. So self-consistently evolving what the metric is doing according to the dynamics of the fields, okay? And so, you know, if you want to study very small effects, which is the things that I'm largely interested in, you need very accurate codes. So just a quick advertisement that, you know, I wrote this big 3D lattice code quite a while ago. Using a bunch of numerical tricks, you can get machine precision, both for time dependence and spatial dependence in your solutions. Okay. So this is like as accurate as you're ever going to get with a computer. Okay. All right. So what does this look like when you actually go ahead and solve? So here I'm showing an actual example of an end of inflation simulation. So what I've got here is a box that is roughly 1 Hubble volume at the end of inflation. Okay. And I've started with, you know, some mean field with some small fluctuations around it, and it starts oscillating. And what I'm plotting is the log of the energy density as a function of time. Okay. And so what you can see, maybe I'll just let it reloop, is initially the thing is very homogeneous, you know? The density is basically the same everywhere, okay? And now you can start to see fluctuations growing. And these initially are standing waves, which is the linear instability. And at some point you get like wave breaking phenomena. And what comes out of that is a very complex looking medium where you have these huge order 10 density fluctuations all over the place, okay? And so we think that this is like the first stage of how you transfer energy from the inflaton into the standard model particles. And this is kind of a bunch of particle production in your simplified model of scalar fields. Now, I do also want to point out that something very wild is happening here, right? So the state that I end up in with these order 10 density perturbations, those density perturbations are quantum fluctuations, okay? So what we're saying is we started with the vacuum fluctuations. They underwent dynamical evolution and interacted nonlinearly. And what I get out is like a classical distribution of huge order 10 density fluctuations. Okay. So when you think about what's being done, it is very, very wild. And as I'll get to in a bit, I think it's worth questioning whether we really understand how to do quantum field theory in this regime. Okay. All right. So that's preheating. And I just want to quickly talk about one other dynamical phenomenon that involves a nonlinearity in the system. And so that's these other two epochs that I pointed out, which is sort of the phase transitions that may have happened as the universe is cooling off, and the fact that our entire observable universe might exist inside a bubble that resulted from a phase transition. Okay. And so both of those epochs have the same dynamical feature that they're first order phase transitions that are happening. And so again, a toy model for how to think about this is I'm still going to stick to the regime of relativistic scalar fields, but now instead of having a potential with a plateau and like a minimum that I'm going to oscillate around, instead I'm going to have a potential that has multiple minima, and in particular, one of them is going to be a local instead of global minimum. So it's a false vacuum. It'll be a metastable state. And we're going to imagine that somehow we've managed to stick a large region of the universe into this metastable state, so into the false vacuum. So there's a large spatially extended region that's sitting in the false vacuum. Now, classically, the thing could just sit there forever, okay? Solve classical equations of motion. This is a solution, 0 equals 0, we're happy. But in the real world, things don't work that way. You can, of course, have thermal fluctuations, which can kind of cause the thing to fly over the barrier. You could have some external perturbation come along and kick it out of the minimum. Or the thing that I'm really interested in is you can have quantum effects that will cause the field to tunnel out through this barrier and out onto the other side, okay? And the usual interpretation of this is as a quantum tunneling effect, although there are ways to get this via classical time evolution. So I think this interpretation is still maybe not entirely solid. Anyway, the way that this is really supposed to work, if you were watching the system, so you start in the false vacuum, is you will see a bubble nucleate. And inside the bubble, the field will be sitting over near the true vacuum, and then outside the bubble, it's still in the false vacuum. And then as time goes, you'll nucleate more and more and more bubbles. And then depending on whether or not you have an expanding background that you're sitting in or not, the bubbles might coalesce and eventually lead to a completion phase transition. Okay. And so what does this look like in action with actual simulations of scalar fields? So this is just another numerical simulation. This is a slice through a 3D box. So white is the field is sitting near the false vacuum, and I put in little quantum fluctuations again. And so red and blue are the field sitting instead near the true vacuum in the potential, okay? So I start with these vacuum fluctuations and I hit go, and you can see the system forming bubbles that then expand out and eventually coalesce and collide with each other, okay? So this is what I mean by vacuum decay. And as you can see, again, we're getting like huge order 1 changes to the field. So this is a really, really nonlinear phenomenon that's happening. Okay, so you might say, okay, that's nice. Okay, nonlinear physics. Why should I care? And to that, I'll say there's a few reasons. So one is nonlinear physics and non-equilibrium physics is just cool. And if you look at the world around us, most things are not in thermal equilibrium. The world is an inherently dynamical thing where we're not discussing equilibrium physics, we're discussing non-equilibrium evolution. And so this is really fundamental to our understanding of the world, including cosmology, because the universe is not a static system. And also in the early universe context, this is a regime where we have an intersection between nonlinear quantum field theory and gravity. So it's potentially giving us a window into the way that quantum gravity works, in much the same way that inflation gives us a window into sort of linearized quantum gravity. Okay. If that's not the theory motivation doesn't appeal to you, well, I would say there's other reasons. So our current standard model of cosmology is incomplete if we don't understand these things. Specifically, we know that something like preheating had to happen if you want to connect inflation to the standard hot Big Bang. And so if you say, I don't care about understanding this epoch, you just say, well, I've got my cosmological history, there's this big white band, and I don't know. Okay. And similarly, if you say, I'm not going to worry about the Big Bang, okay, well, once again, you're taking a part of this cosmological history and saying, I'm just not going to worry about it. It's a black box that I'll never understand. Okay. And also, in sort of the state where the universe is cooling, there's a lot you can learn about particle physics if you can come up with cosmological probes of phase transitions and this sort of stuff. Okay, and I think closely related to that, there's observational considerations for why we should try and understand these regimes of strongly nonlinear behavior in the universe, and that's because they can leave observable imprints that are very different than the ones that we get from standard inflation. Okay, so because they're nonlinear, they tend to be non-Gaussian signatures. okay, which is beyond sort of the standard inflationary prediction. And you can also get interesting gravitational wave signatures and this sort of thing. And so, given that we inhabit only one universe, okay, we're only going to get one look at cosmological observations. We get one CMB, we get one realization of the large scale structure. And so we have these very beautiful data sets. We've observed the CMB temperature fluctuations as well as we're ever going to observe them. We're never going to get another picture unless we have a very long time. And we're going to have polarization data soon. And we also have a huge wealth of large scale structure data that we're going to be getting in the next decade or so. Okay. And at present, as it pertains to the early universe, these very wonderful, complex data sets are basically used to like fix two numbers in our cosmological model. Okay. We kind of get a spectral slope and amplitude on a power spectrum. Okay. And then there are some other constraints on things like the tensor to scalar ratio, or some perturbative measure of how non-Gaussian the fluctuations are. But really, we're taking this very complex, rich data set and just trying to use it to grab two numbers. Okay. And given that we're not ever going to get another data set, there's only one universe we get to observe, I think it's worthwhile to ask, what else can I use this data for? Are there other things that I can search for? Of course, the danger is that you do some data mining exercise, and then because you've only got one realization, sure, there will be statistical fluctuations in it. And if you don't have a good basis for what you're looking for, a good theoretical basis for a particular pattern, it's hard to really prescribe much significance to it. But if you can understand sort of these dynamical processes in a very early universe, it gives you theoretically motivated templates to go try and match with your data. And given well-motivated theory templates that follow from like, here's my Lagrangian, I solve equations, okay? If you see a signal, it's much more, you're going to tend to believe it a lot more than if you just do like a pure data mining exercise. And it also allows you to place constraints on these scenarios, okay? And so I just want to point out that, yes, it is possible studying nonlinearity in the early universe to get really interesting signatures that are not within sort of the standard framework that people use to study non-Gaussianity. Okay. All right. So hopefully that's good enough motivation for why we should care. Okay. Now the problem is we want to understand the early universe, but as I've tried to point out, a lot of the interesting things are sort of nonlinear, non-perturbative, non-equilibrium, quantum field theory coupled to gravity. So it's a horrible, horrible, horrible sounding mess that we don't really know how to do properly. Okay. And so all of our understanding of these processes is based on reasonable approximations and assumptions about how to do quantum field theory, but they've never been experimentally tested. Okay. And so we always feel much better about our theoretical methods if we can compare them to an experiment and be like, yes, the theory matches what the experiment tells me, as opposed to just saying, my theory has to be correct, but I have no way to calibrate it. Okay. And so this is where analog systems come in. As I said, we have these theory tools, but they're approximations to full quantum field theory because we can't do full quantum field theory. So what you would like is you would like to find an actual quantum mechanical system that is a field theory. So it's a mini particle system, and you look at like collective modes of the system and behaves as a relativistic field and has some of these dynamical features of things like preheating and false vacuum decay. And so the one that I'm going to talk about here is Bose-Einstein condensates, which are, there are certain special atomic species that if you cool them down to very, very low temperatures, you can get to condense into this quantum mechanical state that really is a field. Okay. And then if you can do that, you have an experiment with a quantum field where you don't have to make approximations for how quantum mechanics works. It's in the system. And then you can do theoretical calculations of how you think that should behave that are making the same assumptions as the theoretical calculations that you're doing of the early universe. Okay. And so, there's a variety of ways you can imagine doing these analog systems. Perhaps one that you've maybe heard of is doing analog Hawking radiation. Okay. And so this is setting up one of these BECs to have a sound horizon and then studying what happens to propagating fluctuations as they fall behind that sound horizon. So those are very interesting. The thing is, what they're doing is reproducing the linear equations of motion for the quantum fluctuations, okay? And so it's sort of a test of linearized quantum field theory, which happens to be the one regime where we have a pretty good handle on how to do QFT. Other things you can use analog systems for is, these are nonlinear field theories. So you can get lots of really interesting, complicated nonlinear objects like solitons. So these are nonlinear objects, but they're classical. Okay, so you don't have the quantum when you're doing this. And the two things I'll discuss in the rest of this talk are, one is the preheating, which if you want starts as a linear quantum mechanical phenomenon, but then through dynamics transitions into a highly nonlinear and we think very classical system, okay? So now we have nonlinearity and quantum mixed together somehow. And then the other one is bubble nucleation, so first order phase transitions, which is a intrinsically nonlinear and quantum mechanical problem, okay? And so in that case, all bets are off as to whether or not we know how to do QFT or not, okay? All right. So I said BECs are a good place to look. The starting reason is they're quantum fields. Okay, fantastic. Now, the problem is a BEC is okay, so how do we go about actually generating a BEC and one that will behave as an effective relativistic field? So here's a quick theorist view of how one does this. Okay, and experimentalists can tell me there are many subtleties that make this much harder than it looks, but okay. From a theorist point of view, okay, let's pretend this can all be done. So what I want to do is I want to find, I'm going to take two different BEC systems and I'm going to cool them both down to a very, very low temperature. So they're going to condense into the Bose condensed state, okay? And so now I have these two BECs happily sitting together and they're not talking to each other, okay? And then I'm going to come along and I'm going to couple them together. And for the specific system that we've been thinking about, this is basically done with a radio frequency laser. But depending on the experimental setup, this can be done different ways. And the point is, this coupling will allow one species to directly convert into the other one. Okay. And in doing this, we are able to make effective relativistic field theories that have potentials for them. And I'll show how that works in a second. So for those of you who are not familiar with BECs, there's a very important scale in these systems, which is called the healing length. And this is basically the length scale where the dispersion relationship for linear fluctuations goes from being a wave-like relationship, so linear, to being a particle-like dispersion relationship, so it's quadratic in wave number. Okay. And because we want relativistic fields, we're really interested in the limit that we're looking at length scales much larger than the healing length. Okay. So if you want, what we're really trying to do is there's some experiment, okay? And then we have some equations that we think describe this experiment. Now, there can be lots of complications in going from an actual physical experiment to theoretical modeling of it, but let's pretend we've worked all of that out. Now, the amazing thing that happens is we have this equation that is usually used to model Bose-Einstein condensates. And so this looks like a Schrodinger equation, okay? We've got, IH bar psi dot equals a momentum squared term from all of the individual particles. We're building these things in a lab, so we have to build the BEC in some external trap, okay? So this is the potential energy from that trap. And then there's an additional term that is capturing the effects of scattering between the particles, so 2-to-2 scattering, okay? And so if I just had this stuff, this would be the nonlinear Schrodinger equation. And then I said I wanted to couple my two BECs together. That's adding this extra term here, which is a coupling nu that directly will convert species I to species J, okay? And so this looks like a highly non-relativistic thing, okay? And the amazing thing is, lurking inside the dynamics of this equation is an effective theory for a degree of freedom whose Lagrangian looks like this, okay? And this is, of course, the Lagrangian for a relativistic field with a cosine potential, okay? And so the fact that this mapping from the BEC to this effective degree of freedom exists is the reason that we can use BECs to simulate the early universe. Because the early universe, nonlinearity in the early universe is really based on assuming these types of models for what the universe, for what the dynamics of the early universe is being driven by. Okay. Now, of course, we don't have gravity in the system. That's a separate issue, but we can still study sort of just non-equilibrium, nonlinear quantum field theory by itself. And then, we already don't understand that. Once we understand that better, we can start to like treat gravity in a more precise way. Okay. All right. So this might seem very surprising. Okay. I've taken this very, very, very non-relativistic equation and claimed that it's really doing relativistic things. So how does that work? Well, as a first hint, I already said, if I go to very long wavelengths, I get a dispersion relationship that will have this form, okay? So if I just take fully linearized fluctuations of the BECs, okay? And if I take k to be much less than the healing wave number, I get omega squared is m squared plus k squared, which is a relativistic dispersion relationship. So there's a hint there already that maybe we can do relativistic field theory with these things. So how do I do that in more detail? Well, my usual description of the BEC is some complex number, well, some complex field, okay? And if I rewrite it in this other form, okay? So I have a modulus and a phase, okay? And the physical interpretation of this prefactor rho here is the local number density of particles in the condensate, okay? So it's a very physical thing. And then the phase is a phase, okay? So if I assume that I've condensed my BEC, so I have a bunch of particles actually sitting in the BEC. So there's some background value of this rho, and then there are small little fluctuations in the number density in different positions, in different places. Okay, and I assume these are small. I can then expand my action in these little number density fluctuations. And I'm not going to make any assumption about the size of fluctuations in phi. Okay, that's the key thing. So if I do that, I expand my Lagrangian, and then I make a change of variables. So instead of studying the phases of the individual condensates, I study the relative phase between them. Okay. And then I integrate out these number density fluctuations. What I will find is that for this relative phase variable, I get an effective Lagrangian that looks like this, okay, which is the Sine-Gordon equation. All right. And so if I just study what is the dynamics of the relative phase between my two coupled BECs, it will behave as though it is a relativistic scalar field with a cosine potential. And that's super interesting because it's very well known that the Sine-Gordon model possesses preheating dynamics. So, I have a cosine potential. If I displace the field from the minimum and let it start oscillating, there's a band of exponentially unstable modes in linear perturbation theory that will grow and eventually become nonlinear. Okay. Before I get to that, I just want to do a very quick aside, off into the other topic I had brought up at the start, which was false vacuum decay. Okay. So far I've told you how to get a cosine potential. Okay. But that clearly does not have a false vacuum in it. Well, if I go back and look at my equation here, so I've got this nu. Okay. And remember, that was the coupling. This externally imposed coupling between the two condensates is parameterized by this. So what I can do is I can make this thing oscillate in time. Okay, so I can modulate the amplitude of that coupling. Okay. And what I have here is the Sine-Gordon model. Let's throw away the gradient term and just assume it's a zero-dimensional thing. Well, that's the Lagrangian for a rigid pendulum. Okay. And now I'm going to oscillate the length of this pendulum, which in some approximation is equivalent to oscillating the pivot point. Okay. And so what is a rather interesting thing about the rigid pendulum is that if you make the pivot point oscillate, you can make it stand vertically up and down and undergo oscillations. Okay. So what that means is you made at least a locally stable minimum for the pendulum standing vertically. Okay. And so applying this same logic to the BECs, you can say, okay, I'm gonna allow this coupling between my BECs to oscillate with time, and I expect that to create a false vacuum. for when the two fields are, in this case, pi out of phase with each other, okay? And so you can go ahead and you can do a calculation to show this. So assume that you vibrate it very fast, okay? And then you want to study the dynamics of the much more slowly evolving long wavelength mode. So you kind of you integrate out the fast time behavior, and you get an effective potential for the slow modes that actually does have this form that I can grow a local minimum in it, okay? And then experimentally, I can also set up my experiment so that I put the field, the relative phase between the two condensates, so that it's sitting in this false vacuum, okay? So that means that I could do false vacuum decay with these BECs. And remember, this is a relativistic field, okay? So if I can now cool it down to 0 temperature, I will literally be studying quantum bubble nucleation and decay of the false vacuum via quantum effects with an experiment, okay? All right, and so then you can do numerical simulations of this just to see if this, like, you know, hand wavy theory is actually correct. So what I'm doing here, I've got this parameter lambda, which is proportional to the amplitude of the modulation in that coupling constant I had in the BEC. Okay, and as I take it to, as I make it 0, I'm at a local maximum here. When it's equal to 1, I have an effective quartic potential at the maximum, and then if it's bigger than 1, there's actually a local minimum. So what I'm doing on the, as I move from the top to the bottom, I'm increasing the depth of this minimum, okay? And so if I have no modulation, I've just put this particle at a local maximum, so it undergoes a second order phase transition, there's a spinodal instability. As I start to make that effective well deeper and deeper and deeper, oh, sorry, one other thing I should point out. So blue here is the field is sitting near the false vacuum, and red is it's sitting near the true vacuum, okay? As I make the potential deeper and deeper and deeper, what I see is I start to get something that looks like bubble nucleations that are very fast. And if I make the well deep enough, I get really well-defined nucleations of bubbles out of the quantum vacuum, okay? And so this is actually a system that's undergoing a first order phase transition, at least using our theoretical tools, okay? And then the really, really exciting thing is that we are currently in the process of building an experiment to actually do this. And so we will be able to hopefully see a relativistic false vacuum decay using an actual laboratory system. And we can then compare that to our theoretical calculations that are really making the same assumptions that we make in the universe and use that to calibrate our early universe simulations for cosmology. Okay, so after that small detour, back to the regularly scheduled programming of preheating. Okay. All right, so as I said before, there's some limit we can take where the relative phase between our two condensates looks like a sine-Gordon field theory, okay? And so now, okay, as I said, it's very well known that if I take a field and let it oscillate around, okay, I've got this effective potential here. I'm now going to displace the mean field from minimum and let it oscillate, okay? And so, first of all, I said I'm supposed to get a sine-Gordon equation back. So in the top left here, I've got a phase diagram for phi and phi dot. And the solid lines are solving the full BEC system in the homogeneous limit. The dashed lines are just solving the sine-Gordon equation, okay? And so you can see as long as the amplitude of the oscillations is not too big, the sine-Gordon approximation is actually a really, really good approximation to the dynamics of the background BEC evolution, okay? All right, so now I've got this field oscillating around the minimum, and it's supposed to have little quantum fluctuations around it, okay? And so I can study the dynamics of those perturbations, which is the linear part of the preheating calculation. Okay. So again, it's convenient to, instead of using the fluctuations in the individual complex variables describing the condensates, to look at a total phase, a relative phase, a total number density, and a relative number density. When you write down equations, they look like this. Don't worry about exactly what is in these equations, okay? The important thing is this pi bar and this phi bar are the background. So this background that I solved here, okay? And they're undergoing oscillatory motion. So this equation has the form of dy dt is some linear operator times y, where the linear operator is periodic in time. That's the only important thing, okay? And so it's very well known that if I have an equation of this form, the solutions will take this form, where P is some periodic function, and mu is an in general complex number, okay? And mu will depend on like, the K in here, exactly what the dynamics of the background are. Okay, it depends on some parameters. But anytime I have a positive real part to the mu, it means I have exponentially growing modes in my system. Okay? And I can also take the limit of these equations where this coupling between the two condensates is small, which is the limit I want to get into the relativistic regime. And in that case, I reproduce what is the linear perturbation equation for the sine-Gordon model for the fluctuations. And recall that the background is also following the same evolution as under the sine-Gordon equation. So I'm really replicating the linear perturbation equations in the sine-Gordon equation. So now, it's obviously of interest to compute what this exponent is as a function of wave number and model parameters. So you can do that. It's just a linear calculation. It's quite easy to do. What I've done here is shown it for a range of choices of this coupling between the two condensates and a particular choice of the amplitude of the background oscillation. I just want you to note that the dashed line is the sine-Gordon prediction. And then we can see as we take this mu tilde parameter to be small, I basically will reproduce the sine-Gordon predictions as I would expect. Okay, you can do it for different amplitudes. You find very similar results. Okay, all right. So that's all great. So now you might ask, what about nonlinear dynamics in the system? Because, linear theory is great, but really nonlinearity is the more interesting thing. Okay, so what I've got here is assuming I have an effective one-dimensional Bose-Einstein condensate. And what I'm doing, I'm solving the full couple Gross-Pitaevsky equations. And what I've done is I've displaced the relative phase of the fields and put some small fluctuations on top. And we can see the evolution in the left panel here. So the field's just oscillating back and forth as you would expect. And now you can start to see the growth of a standing wave, which is the linear instability. And now it's going to basically undergo wave breaking and nonlinear evolution, where we get mode-mode coupling. Okay? And so what we see is this initial exponential linear growth of fluctuations that eventually hit the mode-mode coupling regime and become very nonlinear. And in this particular case, what will happen is we end up with these persistent sort of oscillating peaks in the field that are very closely related to a solitary wave known as an oscillon. Okay. And you can go ahead and compare, you can extract from these simulations the growth of various Fourier modes and compare it to your linear perturbation theory prediction. You find very good agreement at early times. And then at some point, nonlinear effects start to be important, and the growth rate of modes in the instability band will change, and also modes that were initially outside of the instability band will also start to grow. So that's the first stage of nonlinear interactions. Okay, it works if I change the number density of particles. So I'm sort of more into the very strongly quantum regime. So it's robust to some experimental changes. And we can similarly do it for a 2D system instead of a 1D system. So this is just showing the same thing. I start with a mean field oscillating back and forth. And just to avoid having some hallucinogenic colors going on, I removed the evolution of the mean field here. So you're just looking at what the fluctuations are doing. Okay, and so we can see the emergence of standing waves. And very soon, some of these peaks are going to get big, and you're going to see them emit bursts of radiation. That's the onset of strong nonlinearity in the system. Okay. So that's all great and wonderful. Okay. Fantastic. Okay. The problem with what I've done here is I assumed everything was spatially homogeneous. Okay. And as I said at the very start, in real BECs, we have to trap them in a potential. Okay. And that means, from the viewpoint of this thing, assuming the background is homogeneous, is the background will end up becoming inhomogeneous. Okay. And so I will quickly skip over this because I'm running out of time. So what you could do is you could imagine in order to get an effective 1D system, I'm going to trap my BC in a ring. Okay, so I'm going to strongly confine it in 2 dimensions. Okay, and I'm going to allow it to be periodic in the other direction. Okay. And now I'm going to just do the same thing. And I'm going to evolve that system that's trapped, but has an elongated direction, and ask, do I still get the same preheating dynamics happening? Okay, and so this is an example of that. The trapping direction here is the vertical direction, and then the extended longitudinal direction is the x-axis. And once again, you can see the emergence here of standing waves along the longitudinal direction that eventually wave break and undergo very strong nonlinear interaction, but I continue to have these strong peaks that oscillate up and down in the field, okay? And if I reduce this to an effective one-dimensional evolution, I get things that look very similar to just running the one-dimensional Bose-Einstein condensate simulations. Okay, and so it looks like the preheating dynamics is at least robust to some types of trapping of the BEC, which are required for a more realistic experimental setup. Okay, so given I'm out of time, I will stop here. So what I hope you took away from this is, number one, the early universe is full of really interesting nonlinear dynamics that required us to understand non-equilibrium, nonlinear quantum field theory. Okay. And the really exciting thing is that you can use some coupled dilute-gas Bose-Einstein condensates to really replicate a lot of the dynamical behavior that we think may have been going on in the early universe. And there are ways to mimic specific epochs, specifically end of inflation, and so preheating, and anytime you have phase transitions and false vacuum decay of a relativistic field. And then, you know, I did some more detailed calculations. You can see that in linear theory, the BEC calculation and the relativistic theory, so cosmological calculation, match each other, with deviations being controlled by an experimentally tunable parameter. In the nonlinear regime, you end up with solitary waves, all kinds of really interesting behavior. And all of this persists, sort of starting to take into account some of the complications of real experiments, such as trapping of the BEC and this sort of thing. Okay, so I'll end there, and hopefully I gave you a flavor of what this field is about. And please ask me questions either offline or in the discussion session. I'm always super happy to talk about this sort of stuff. So thanks.